Hello, welcome back. This is lesson 6 in our 20-1 quadratics. You'll find the links exactly where you find them for all the other ones. You'll have a blank copy and the solutions. This time I'll talk about one of the forms of our quadratic equations, standard form, as opposed to general form. So there's two types. You've seen it before in some of the other videos here, so I'll throw them in the top. This one is more familiar for those of you coming from Math 10, which we would call general form. Right? And we can factor these, sometimes we can't, but most of the time in Math 10 you could factor things. We started to talk about factoring here as well. The other form is y equals ax minus p squared plus q, which will be standard form. Right, it tells us a little bit more information about our equation. It's going to really tell me what the vertex is. General form really doesn't tell me anything about it other than the direction it opens. But standard form, there'll be more, there's more use we can get out of it. We can describe some of these transformations here. So A, B, and C is like what we talked about in the last video. So if we go to describe some of those transformations again, remembering the order we're going to do it is stretch, reflect, translate. That way I know that for A, this negative sign is going to tell me I've got a reflection. Right, so we've got a reflection in the x-axis. Let's say reflection over the x-axis. And the number attached to that x there will tell me I've got a translation. So this is going to be a horizontal translation, 5 units left. For B, again, stretch first. So we've got a vertical stretch by a factor of 3, because that's the number in front of our squared term. That'll always be the number that tells us our stretch. We also have a vertical translation this time, 4 units down. For C, the last one, we've got a bunch of things happening all at once. So stretch first, we've got a vertical stretch by a factor of 1/3. There is a reflection as well. So reflection over the x-axis. And we've got translations of 4 units right and 6 units up. Okay, so stretch, reflect, translate, just like we talked about previously. Well, now let's try to do some algebraic things with this, like finding some intercepts. So we talked about those intercepts and how important they were before. Really, it's the basis of this whole unit. So if it's the x-intercepts, you can call them zeros, solutions, roots, zero, solutions, roots, or x-intercepts. All 4 of those things mean the same thing. And we're asked to do this as exact values. So given the form that it's in, I don't want to do decimals or anything like that. And I don't really have to factor it. So there is another way that we can do this, and it uses the idea called isolation. So really what you're going to do is get your variable by itself, is the goal. So let's go do the y-intercept first. It's a little bit easier to think about. Okay, so the y-intercept. Every single one of them has the same thing in common in the sense that x has to be equal to 0. So we'll take our function f, we'll put in 0 for x, the input, so we'll get 0 in x, and we can solve for this pretty easily. We can solve for y. So 0 minus 1 is minus 1, it gets squared, you've got a minus 9, so negative 1 squared is 1, times 3 is 3, so 3 minus 9, and your intercept is going to be negative 6. So therefore, when x is 0, y is negative 6. So I've got a y-intercept, but now I have to go get an x-intercept. And again, the same logic is true, except y is going to be 0 this time. So when I put that into the equation, well, I'm going to have 0 equals 3 multiplied with x minus 1 squared minus 9. And it makes it more challenging because there's an x that's being squared. So I might have two answers if I were to factor it. You could have one. You could also have none. Like we talked about, there are 3 cases. So the idea that works here is isolation. So we're just going to get x by itself. So opposite operations is what we'll take care of. So we'll add a 9 to both sides. That'll cancel those out, move them over. So 9 equals to 3x minus 1 squared. If you then divide by 3 as your next step, you'll see that 3 is equal to x minus 1 squared. Well, in order to get rid of the square, we're going to square root both sides. And this is where the logic needs to change a little bit, because as soon as you square root a number, technically you get 2 answers. Right? Think about square rooting 4. Right? Your calculator will tell you it's positive 2, which is true, but negative 2 can multiply with itself, which is negative 2, to still give you 4. So there's 2 answers. Always the positive and negative root of something. But 3 is not a perfect square number, so we'll leave it underneath a root sign. So plus or minus the square root of 3 is equal to x minus 1. In order to get x by itself, add a 1 to both sides, but you can't add the 1 to the 3. The 3 is locked under a root sign. The rules aren't the same for adding. So think about doing the square root of 3, pressing enter on your calculator, and then adding 1 to it. So really I get 1 plus or minus the square root of 3 is equal to x. So there are my 2 solutions put together. If I were to split this up, x could either be 1 plus the square root of 3, or x is equal to 1 minus the square root of 3. There's 2 different forms here, and if I were to put it in a calculator, what you'll see is it's either 1 plus the square root of 3, there's one number, or 1 minus the square root of 3, there's the other. So I have 2 solutions here, and I could do it graphically as well. Let me open up a Desmos tab here, and we'll type it in. Okay, so here's a graphing calculator. It just makes it a little easier, a little faster to graph this. So there's our equation off on the side here. So 3x minus 1 squared, x minus 1, using my keyboard clicking away probably, minus 9. So my 2 x-intercepts are right here, just like we said they were going to be on my calculator, right? So 1 minus negative square root 3 is negative 0.732, there it is. The other one on the other side, 2.732. This is the same numbers. So you can see that there are 2 definite solutions to this, but they aren't whole number factors like we talked about before. So factoring wouldn't even have worked here if I tried to multiply things out. Okay, so isolation is something that can work as well. So let's go see if we can find an equation if we're just given some information. So I'm told here that I'm going to look for the equation in standard form, and I know that the vertex has some coordinates, negative 1 and 2, passes through this point 3, 1. Now if you're ever told a vertex, really you're told what P and Q happen to be, and in our standard form, here's what it looks like. Y equals A, x minus P squared plus Q. Some sources will use, instead of P and Q, they'll use H and K. The variables are irrelevant. The numbers don't change. Right? You can change the variables to be whatever you want. They'll still go in the same place. And if you have just a coordinate point, well, really you know an x value and a y value. If you think about all the variables you have here, you have 4 of them. You have 5 variables in total. You were just told what 4 of them happen to be. So plug everything in, and you can get the last one that's left. Right now, I don't know what the stretch is. I don't know if it's a negative, if it opens up or down. I don't know if the value is something other than 1, so I have to find it. So we'll plug those numbers in. So here's our equation. Y equals ax minus p squared plus q. And I know that if I put all the numbers where they're supposed to be, 1 is going to be y, a is unknown, x is minus 3, there's a negative built into the equation, p is minus 1, gets squared, and I'm going to add q to it, which is 2. Everything's where it's supposed to be. Our only job now is to simplify and solve for a. So 1 equals a, in brackets. Negative 3 minus negative 1 is negative 2. Negative 2 gets squared to give us 4. And I've still got a plus 2 on the end. If I combine them, if I move the 2 over, you're going to get negative 1 is equal to 4a, so that negative 1 over 4 is a. So now I know I've got both a stretch and a reflection happening here. The stretches factor 1/4. The reflection tells me the negative. So if I go to make my equation now, y is going to equal negative 1 over 4, x minus p, which is really x plus 1 here, because the negatives will cancel, and add the 2 on the end for q. So there you go. And again, we can try to graph this in our Desmos tab here, just to make sure that the information checks out. So here's our equation. Negative 1/4 x plus 1 plus 2, that's squared first, and then plus 2. And the point we're looking for, well, there's my vertex, negative 1 comma 2, that's what I'm supposed to have. The other point that's supposed to be on here is negative 3, 1. So you can enter another equation into there, and we'll put the coordinates of negative 3, 1, and you can see it on the graph as well. So I've got my vertex, got my point, I know my equation is correct. I have everything where it's supposed to be. So that's all good. We've got to go find the x and y intercepts as exact values. So I know it's not something that's factorable based on the form that it's in. So let's take a look at how to solve for them again. So I know what my equation is. Y equals negative 1 over 4, x plus 1 squared plus 2. So let's go see if we can solve for x. If I make y 0, again for an x-intercept, everything else stays the same. So I know that I'm going to have negative 2 on the other side if I move it. And if I get rid of my fraction, I can multiply both sides by 4, multiply by the denominator, and if I use a negative, both things will be gone, the fraction and the negative. So 8 is going to equal x plus 1 squared. If you square root both sides now, you get positive or negative square root 8 is equal to x plus 1. Subtract a 1 from both sides, so negative 1 plus or minus the square root of 8 is equal to x. If you go to simplify this root sign a little bit, which you can do from Math 10, 8's the same thing as 4 times 2, and to remove that 4 from your radicand, you can square root it. So really this in its most simplified form is negative 1 plus or minus 2 root 2, which is equal to x. Okay, so you are going to get a decimal, and if you graph it, you'll find out what the values happen to be. I just want it as exact values, so we don't need the decimal. Now if I go to find the y-intercept, this time we're going to make x equal to 0. So put in a 0 for x, add 1 to it, it's still squared, plus 2. So y equals to negative 1 over 4. 0 plus 1 is 1, squared is still 1, plus 2. My y value is, well, whatever 1/4 plus 2 is. 2 as a fraction out of 4 will be 8 over 4, so this works out to be 7 over 4 as your y-intercept. Okay, so I found my two things. Rewrite in general form. So I was given it in standard form. Okay, let's rewrite it in general form. So I can take that general form equation we had from before, and I can multiply everything out. So let me zoom in a little bit here. Negative 1 over 4, x plus 1 squared, plus 2. And let me fix that. X plus 1 squared, plus 2. In order to get it into general form, we can multiply this all out and then collect our like terms. So if you remember how to multiply out a perfect square, well, you can square the first term. You take the two terms that are there, so x and 1, multiply them together and double it. So you get 2x, and there's a plus 1. Saves you a little bit of time in collecting like terms. Distribute your fraction to the inside. So you get negative 1/4 x squared plus 1, not plus, minus 1/2 x minus 1/4 plus 2. If you collect your constants together, you'll have your y-intercept from before. So it was, I believe, 7/4 as a positive. And there is our equation general form now. And one of the ways that you can double check that you've done this correctly is to graph the original and also the new form you think it is. So if I graph this, I really should see the same picture. If I see something different, then I know that something I did is incorrect. Something I did obviously doesn't work out. Let's see what I forgot. I think I wrote this as a 1/4, but it's supposed to be a half. So let's change that. And we'll change it in our green equation in Desmos here, and that's much better. So I can see that they overlap. So I know that these are the exact same graph, the same parabola, equations just different. So I know I have my two forms. Okay, if you think about example number 3 here, same sort of question, but determine in standard form again the equation of a parabola with an axis of symmetry, x is equal to -3, that goes through the 2 points -4, -8, and -1, -20. The problem with this one is I'm not told what the vertex is. All I know is I have part of it. So I know that the symmetry line is x equals 3. So x equals -3, sorry. So that means p is going to be -3. And really, that's what I'm told here. I know I have 2 coordinates, so we're going to have to do this 2 times and set up partial equations to see what I actually know. So we'll do the first one in blue. So let x equal -4, y equal -8, p is going to equal -3, and we'll see where that'll get us. So if y equals to ax minus p squared plus q, then I know that -8 should equal to x is -4, p is -3, so really this is +3 in here, and I don't know q. So if I simplify that, I get -8 is equal to, well, -4 plus 3 is -1, squared for +1, so this is just a plus q. And that's about as far as I can go right now. So we'll do the same thing with the other coordinates that I'm told, and see if I'm able to figure something out from there. So if I try this again, same sort of pattern, same sort of process, I will let x equal -1, y equal -20, p is still going to be -3. It's the same parabola, there's just 2 different points that we're looking at. So the symmetry line's the same. And if I do that, well, I know that same form, ax minus p squared plus q. So I know that -20 should equal -1 plus 3 again squared plus q. So if I simplify that this time, -20 stays, -1 plus 3 is 2, squared is 4, so 4a plus q. Okay, so I have 2 equations now that use common variables. That's the literal definition of a system of equations. So I can think about eliminating a variable here, and as long as one of the variables has the same coefficient, doesn't really matter if they're positive or negative, but the same number in front, I can get rid of them. So if I take -8 as my first equation, I'm just going to put it on top of the other one. And again, the order that you do this doesn't matter. I could have easily written them in the reverse, but I'm going to take one equation away from the other one. And what that will allow us to do is get rid of one of our variables. The q is going to disappear here, so I'm just going to be left with an equation I can solve for a. So -8 minus -20 ends up being 12, and that's going to equal to -3a once I subtract my a's. Q minus q will be gone, so now I know the value of a is going to be -4. Well, now that I know what a is, I know what a is in every single part of this question. So if I take a and put it into my blue equation, well, that's just the one I chose to find out what q is. So -8 is equal to a plus q, but I know that a is -4 now. So in order to find q, I'm going to add 4 to both sides. So now I know that -4 is also my value for q. I know what a is now, I know what q is, so I can write my quadratic equation as -4 x plus 3 squared minus 4. I now found my two missing numbers. A is -4, so I know there's a reflection and a stretch. Q is also -4, I know it went 4 units down, comparing it to the original y equals x squared. Okay, so we found everything we needed to. If you were to graph this, you'll see these 2 points on there, and the symmetry line should be -3. So it gives you a way to double check it, to make sure that you know you did this correctly. Okay, so we'll graph it here to check. So y equals -4, x plus 3 squared minus 4. So here's what it'll look like. So there's my vertex, which I didn't know before. Here's my symmetry line. X equals -3, so it goes right through the middle. We wanted one of the points on it to be -1, -20, right? And I can see that red point is definitely on the line. The other point that's supposed to be on here is -4, -8. And you can see that that point is on the line as well. So neither of the points were the vertex, so I couldn't have used them for P and Q, which is why I needed the symmetry line to tell me that it's -3. So everything is true, everything's on there like it's supposed to be, all looks good. Okay, we've got one more to try here. So we'll again build this equation out using the information I'm given. So again, this time I have a vertex, so I know the P and Q values. The other point is just a point, so that's going to tell me x and y. The only thing I don't know here is a. So if I plug in what I know to my equation, ax minus p squared plus q, well, I know the y value 7, so that's going to equal a, which I don't know. X is -1, and we'll subtract the p value, which is -2. That's closed, squared. Q is +8, so we'll add an 8 to the end. So all my numbers are where they're supposed to be. Now we just got to simplify. So 7 equals a, brackets. -1 minus -2 is +1. Squared is still 1. Then we've got a +8 on the end. So if I subtract 8 from both sides, I know that -1 is equal to a. With that piece of information, I can write my equation as -x plus 2 squared plus 8. So I know what my vertex was. I just can throw it into here. A goes into there as well. I've got my equation in standard form. To rewrite it in general form, okay, we'll undo all that work we did to get there, multiply everything out. So if I, multiply out the brackets using my perfect square technique, I know that I've got x squared plus 4x plus 4, plus 8 is still on the end, so -x squared minus 4x minus 4 plus 8. So I know that y should equal -x squared minus 4x plus 4. Okay, so there's my general form. Use your graphing calculator to find out what those intercepts are going to be. Okay, so if I use my graphing calculator here to use my 0 feature, if I graph this, let's clear those out of here. So negative x squared minus 4x plus 4 graph. So there it is. So I know I have two x-intercepts. Second trace, 0. Move your cursor around. So we want the left boundary. Cursor is underneath our intercept. Hit enter. You can see the triangle comes up on the left. Move it up a bit. Enter, enter. There's one of them. Nearest hundredth if necessary. So x is going to be negative 4.83. Yep, 4.83. The other one, I have to do that whole process again, but on the other side here. And I think it's 0.83 if my memory serves me well. Yep. X equals 0.83. So I know I couldn't have factored this. You can't find two numbers that multiply to 4 but add to negative 4, hence the decimal equivalence here for the zeros. You can find the y-intercept as well. Second trace, but you're going to enter a value this time. The y-intercept isn't a 0. It has an x value of 0, right on the axis. Hit enter, and you've got your y-intercept of 4. Right? When x is 0, y is 4. Right? So I've got both intercepts, both the x's and the y-intercept on here. All is well. So I can go make an equation, provided I have some coordinates to do so. Okay, when you come back in the next video, we'll talk about a little bit more about roots and completing the square, which will allow us to go the other direction from general form back to our standard form. Right now I can only go one direction and take my standard form and get to general form because we can multiply things out. Right? I can multiply to go this way. In order to go backwards, I need a process called completing the square. So once I know both of those, once I know how to complete the square, we can go into whatever form we need very, very quickly. Okay, and it'll be something we use a lot in the applications and word problems for this unit, so it is quite important. The last thing we can use to solve some equations is the quadratic formula, and that'll work every single time. So I hope you found that helpful. We'll see you in the next one when we talk about completing the square. So take care, and we'll see you then.